You're joining Mrs. Goddard right now for the very first flipped classroom session. We're about to head into Chapter 5, and we're going to be trying this new kind of setting for all of Chapter 5. Oops. Okay, so like I said, we're doing Chapter 5. All of Chapter 5 has to do with applications of differentiation. So now that we've actually learned how to differentiate, hopefully we've gotten the idea that differentiation is finding derivatives, which is finding instantaneous rates of change. So we've been working with that a whole lot. Hopefully with the applications that we did learn in 4.6, that's starting to hit home. And now as we go into Chapter 5, they're going to just hit home even more. So the specific topic that we're learning in Chapter 5.1 is extreme maximum and minimums. You don't have to write these objectives down, but this is where we're headed. So be able to use and read interval notation, determine the extreme values over a given interval. Extreme values, as you're going to learn, are maximums and minimums. And 3, use differentiation to find critical points, and then relative extrema and absolute extrema. And again, you'll kind of learn some of those vocab words in the slides to come. So why go to the extremes, or why are we trying to find these extrema of a function? There's a lot of reasons for it, but one of the biggest things is in industry, it's always a really huge thing to be able to maximize profits and minimize costs. Alright, so the first thing that I'm going to start us off with is just a quick review of what interval notation is. This chapter uses it a lot, so we just need to refresh it. A closed interval is going to be using those square brackets, and what we need to know about that is it has defined endpoints. So the interval, what this is saying is we're looking at the interval from -1 to 1, so this would include -1, -0.25, 0, 0.25, 0.999, but then 1. And we have defined the smallest value on there is -1, the largest value is 1. Now though, if we look at an open interval, what that is it uses the rounded brackets, and this kind of interval has undefined endpoints. So you'll notice that I did mix it up with a rounded bracket and then a square bracket, but the fact is this is still an open interval, because if I asked you what the smallest value on there is, someone could go ahead and say, oh, well, since it doesn't include 0, what about 0.1? And then I would say to you, well, what about 0.001? And then you would say back to me, well, I can top that, 0.0001. So the idea is, no matter what you say for the lowest value, there is no defined smallest value. It never would end. Just a quick thing on where we've seen this before. We've used it to describe increasing and decreasing intervals of a function. We also have used it to describe domains back at the beginning of this chapter. For example, if you looked at f of x is equal to the square root of x, if I asked you for the domain of that, most normal people would say, well, it's going to be 0 or anything greater. So you could say x is greater than or equal to 0. But us, calculus people, are going to say, well, I could include 0 and go forever after, anything larger than 0. So from 0 to anything to infinity, basically, including 0. So we've seen it there before. Also, we've kind of seen our textbook starting to use it in the last section, 4.5, I believe it was, but it was just looking at some of those average velocity problems, so we've used it. And now your book is just going to use it a whole lot, so just be prepared for that. Just know that it's an interval where we're going to be studying a certain part of a function over the x-axis. So finally, let's get to this. One of the key definitions of this extrema chapter is going to be extrema, and all that is, all extrema are minimums and maximums over a given interval. So there's two types that we're going to be looking at, an absolute extrema and relative extrema. So absolute minimums and maximums versus relative minimums and maximums. So first we're going to be looking at the definition of an absolute extrema, or the absolute extrema definition. This is on page 314. I have reworded it a bit. But what that is we're going to be dealing with some sort of function f, like we normally deal with, f of x. And what we're looking at is we're saying a function f has a maximum at an x value c, so at c, if f of c is greater than all other f of x over that interval. So it's a little bit weird. That's why calculus is dubbed kind of strange, because it is a new language to get used to. Looking at this graph here that I'm drawing, I'm going to go ahead and just draw a sketch like this. Alright, what you'll notice is, let's look at the interval. This is 1, 2, 3, 4, 5, 6. This is going to be the interval from, let's say, 0 to 6. So we're looking at 0 to 6. We're only looking in that window from those x values. So what it spans from is from 0 to 6. And if I were to go ahead and say, well, right here at this value, well, we're going to call it 2. So pretty much in our definition, we're saying there is a maximum value at x equals 2, because if you were to plug in f of 2, well, let's go ahead and say this is equal to 4. This is equal to 4. Well, this output, this f of 2, or in general f of c, is greater than any other f of x value that I can plug in. So that's all this definition is saying. A function is going to be a maximum if that output of that x value is larger than all others. And then likewise, part 2, or I guess on the other hand, part 2 is saying a function f has a minimum at c if, when you look at and evaluate f of c, that value is going to be less than all other y values or output values on that graph. So here looking at possibly 5. So if we looked at, in my kind of sketchy graph here, x equals 5, well, what you notice is if you plugged it in, f of 5, well, yeah, it's going to be less than or equal to all other values up here, because you'll notice that there are no y values that go below this f of 5 point.